Cool. So okay, so what does this say? This says in a directed acyclic graph there will be at least one vertex with no incoming edges. There can be more than one vertex with no incoming edges. There can be at most one vertex with no incoming edges, right? So in a directed acyclic graph, all edges are directed. So there is so suppose you have something like this, 1 to 2 and then 2 to 3, right? Then if there are so there should be a vertex, at least one vertex, which has no incoming edges, right? Because if that is not the case, if all vertices have incoming edges, that means that a cycle will be formed, right? So if all vertices have incoming edges, a cycle will be formed. So that contradicts the fact that the DAG is acyclic, right? Acyclic means non-cyclic, that is no cycles, right? So it should have at least one vertex which has no incoming edges. Okay, or alternatively we can also say that there exists at least one vertex which has in degree 0, right? In degree of v to be 0. So in degree is the number of edges, number of incoming edges, right? So in degree of v is the number of incoming edges, right? So this is required. At least one v should have this. Uh, there can be more than one vertex with no incoming edges. If there is more than one vertex, suppose there are two vertices. So suppose we have a graph like this, and there is say another vertex which has no incoming edges. This is also possible, right? It's also possible for a directed acyclic graph, right? Now for so the second one is also true, right? Because this is also a directed acyclic graph, but this is not connected, right? So in this case it is not connected, but still it's a DAG. It's possible. The third one says there can be at most one vertex with no incoming edges. This is false, and this example is the counter example here, right? If you look at uh, this example, there both 1 and 4 have got no incoming edges, right? And still it's a DAG, right? So here we have the BFS algorithm, right? The BFS breadth first search. What it does is that uh, we have so it goes as the name suggests, it goes breadth first, which means it first maintains a dictionary, right? Visited to keep track of which all vertices have been visited. Okay, and it also maintains a queue, right? To add and remove elements as required. And what is the algorithm? The algorithm runs until queue is empty, right? The moment queue is empty, the algorithm stops, right? And what it does, it looks at the first element of queue, and if it is not visited, then it will add uh, the vertex to the list which is initialized as BFS list, right? And then for each of its neighbors, so this for loop says for each neighbors, okay, for each neighbor of what, of v, for each neighbor of v, if the neighbor is not visited, then it will be added to the queue, right? And then it sets visited to be equal to 1, right? So this is the algorithm, and BFS list will keep a track of what all vertices have been visited. Okay, so now let's look at the first graph, G1. Okay, in G1, if we start from 0, so what will BFS list look like? if we start from 0, the first element to be visited will be 0, right? And the second element to be visited will be 2, right? And that's it. It will stop there, right? It will not visit 3, 4, 1, 5 or 6, right? Because see, the question says for which of the following graphs will this function completely traverse the graph if start from vertex 0, right? And for this it will not completely traverse, right? Because 0 will be visited, then 2 will be visited, but the others will remain unvisited. Similarly, in the second graph, 0 and 2 will be visited, because see, we are starting with 0, right? So again 0 and 2 will be visited, but nothing else will be visited. Now let's look at the third one. So in the third one, what will be BFS list? This will be first 0 will be visited, then we have each neighbor of 0 will be visited, right? Because we are adding the vertices to the queue in that order, right? So a vertex, all of its neighbors, right? And then for each neighbor, each of its neighbors, right? That's how it goes. So first 0, then the neighbors of 0 are 2, 3 and 6. So we have 2, 3 and 6. And then what? Then the neighbors of 2. But 2 does not have any neighbor, so nothing to do. Then the neighbors of 3, the neighbors of 3 are 4 and 5. So we have 4 and 5. And next the neighbors of 6. What are the neighbors of 6? 5 and 0. But 5 is already visited, so you don't have to do anything. 0 is also already visited, you don't have to do anything, right? And then the neighbors of 4. What are the neighbors of 4? Just 3, and 3 is already visited, so you don't have to add. Next, all neighbors of 5. There is one neighbor of 5 which is unvisited, which is 1, so 1 will be added at the end, right? Now we can observe that in one BFS, if you call this function once, right, all of the vertices are visited, right? So G3 is positive in the sense that uh, if you start from 0, all vertices will be visited, right? Now let's look at G4, right? G4 is a directed graph, so again we'll start with 0. Now what are the outgoing edges from 0? We have 2, we have 3, and that's it, right? So let me add 2 and 3. Next we look at the neighbors of 2. 2 does not have any neighbors, so nothing to do. Next we look at the neighbors of 3. What are the neighbors of 3? 4 and 5, okay? Just 4 and 5. 0 is not a neighbor because 0 is, there is no outgoing edge from 3 to 0, okay? So we will add 4 and 5. Now let's look at the neighbors of 4. 4 does not have any neighbors, like no outgoing edges. What about 5? 5 has one neighbor or one outgoing edge, which is to 6. And for 6 we have one neighbor which is 0, but 0 is already visited, so nothing to do, right? So we've covered everything. So this is a whole iteration of the function. So one call of the function gives us this, but observe again that 1 is missing, right? Missing from this list, which means 1 has not been visited, right? So this does not satisfy the condition. Now observe, why was 1 missing? 1 was missing because 1 has no incoming edge. Okay, that is the reason why 1 was missing. Okay. Okay, so here we have two graphs. So two graphs are said to be isomorphic if their number of components are the same. First, that is the first criteria, right? So that means the number of vertices should be same, number of edges should also be the same, right? Then their edge connectivity is retained. What does that mean? That means, so the second condition means that if Vi and Vj are connected in Gx by an edge, connected by an edge in the graph Gx, then the corresponding, so before concluding the second condition, let me rewrite the first condition as this, that there exists So if the number of components are the same, right, we can also say that there exists a bijection f, right, from the vertex set of gx to the vertex set of gy, right. This is something we can say where each vi is mapped to wi, right. So there is a bijection, right. Okay, then uh, basically we say in the second condition we say that in the corresponding uh, wi and wj must also be connected with an edge, right, right. And the third one says, okay, so these are the two primary conditions, and then they say that two isomorphic graphs can have different vertex labels, which means in one graph you can have labels 1 2 3, in other graph you can have labels a b c, right. In the other one you can have say v1 v2 v3. The labels can be different but the structure should be the same. That is the idea, right. Now let's closely look at these three graphs. Okay, the first thing to be observed is that yeah, so first of all we can see that g1 and g2 uh, seem structurally the same, right. Now why do I say that? If you look at g2, I can rewrite this as 1 2 3, right, and then 4 5 6, and then the edges would be in this manner, right, because there is an edge from 1 to 2, right, that comes here. The edge from 4 to 5 actually comes here, right? So you can see that the structure of the graph is maintained, right, and this is the same structure as this, right. So g1 and g2 have the same structure, right. G1 comma g2 have the same structure, or you can say g1 is isomorphic to g2. Okay, what about g3? To see that g3 is not isomorphic to g1 or g2, what we have to observe is that g3 has a cycle. In fact, it has two cycles. Has two cycles. What are the two cycles? One is AEC and the other one is BFD. Both of them are cycles. Whereas G1 and G2 has no cycle, right? That means G3 cannot be isomorphic to G1, or G3 cannot be isomorphic to G2. Okay, this is the this is how we observe that uh, two graphs cannot be isomorphic, right? Okay. Oh. Uh, okay. I think I should make it clearer that has two cycles of length 3. Okay. So this is of length 3. This is of length 3, right? The length of the cycle is 3, right? And G1 and G2 has no cycle of length 3. Okay. Because the cycles are of length, which is equal to the which is equal to 6, right? So in G1 and G3 all cycles are of length 6. Okay, so this is one observation which helps us identify that they are not isomorphic. Okay, so here we have a directed graph which is strongly connected. Now what does strongly connected means? It means for any two uh, pair of vertices, there exists a path from one to the other and the other to the one, right? So you can say for any v comma w in the vertex set, right, there is a path from v to w and there is a path from w to v. That's what it means. Okay, the given graph is strongly connected, okay, and it's directed, okay. Now select the non-crucial edges. Now what is meant by non-crucial edges? That if even if they are removed, we will have the that G is still strongly connected, okay. Despite removal, G will remain strongly connected. Now how to check if 0 1 is crucial or not? So how to check if, say, V comma W is crucial, okay. Again, what we have a directed strongly connected graph. Now how do we check? So first step is remove this edge from the graph, and then check if I can reach W from V through some other path, okay. That is the idea, right? So let's do it. So if I remove 0 1, okay, I will be removing this line, right? And even if I remove this line, I can still get from 0 to 1. How do I do that? Can I still get from 0 to 1, right? Since 0, if I remove this edge, 0 does not have any outgoing edge, right? Which means you cannot go from 0 to n, right? 0 to 1, right? And what does that mean? That means this edge is crucial. This edge is crucial, right? Now let me remove this mark. Now let's see about the second edge, which is 1 comma 2, right? Now if I remove 1 comma 2, suppose I remove this edge, okay, then the question is, can I reach 2 from 1 through other means, right? Now one way is you can go from 1 to 4, right? Then you can go from 4 to 3, but then again you get stuck, right? Or you have to go to 6, but the moment you go to 6, uh, you cannot come back to, there's no way coming back to 3, right? Coming back to 2, right? So why can't you come back to 2? Another reason is 2 now has no incoming edge if 1 comma 2 is removed. What does that mean? That means 1 comma 2 is crucial, right? Because we have a loss in connectivity, right? We lost the connectivity. So you can never reach 2, in fact, okay? You can never reach never reach 2 if this edge is removed, right? So the second one is also crucial, okay? What about the edge 5 comma 9, right? Let me remove this 5 comma 9, and you can observe that even if I remove 5 comma 9, right, I can still reach 5 to 9 through 8, right? 5 to 8 to 9, this is still a path, right? What does that mean? That means the edge is non-crucial, because even if, see, when I remove the edge 5 comma 9, the only vertex that can be affected, right, is 9, right? Because every other vertex is kept intact. So if 9 is still intact, so if we can still reach from 5 to 9 through some other means, then we can reach all other vertices, right? So that is why this is non-crucial, okay? Similarly, let's look 5 comma 0. So if I remove 5 comma 0, right, I can still reach from 5 to 0 through 5 to 8 to 9 to 10 and then 0, right? This is again a path, right? This is a path. So that means I can still reach from 5 to 0, which means this is also a non-crucial edge. Removing this does not make the graph disconnected, right?